Hello, everyone. Welcome back. We are in week 4 of the program, and so far we have covered the basics of quantum computing, and we learned the quantum Fourier transforms and phase estimation. And now we are really going to go deep into the core topic of this year's workshop on how do we solve differential equations on quantum computers. And I'm very excited to invite our speaker for today. We have with us Dr. Nana Liu. Dr. Nana is an associate professor at the Shanghai Jiao Tong University, and she is the PI of the Quantum Information and Technologies Group. She received her PhD from the University of Oxford as a Clarendon Scholar and is a recipient of MIT Technology Review's Top 10 Innovators Under 35 in the Asia Pacific region. She has worked extensively, and she's a pioneering researcher in developing quantum algorithms for scientific computing. And some of you might be familiar with the techniques called Schrodingerization. She's a key developer of the technique, and I'm very excited to invite her to be a part of the Vimanium and WISER program in general, and also to share with us today her knowledge and insights on how do we solve differential equations on quantum computers. Over to you, Nana.
Hi, everybody. So I'm Nana. I'm very excited to be here. And I want to share the work that we've been doing the last couple of years on quantum simulation for PDEs. And I know that the topic of this program is solving PDEs on quantum computers, but I'll mention a bit later how solving is actually different from simulating. And actually, we're still a step away, actually, from really solving them. But I will talk about quantum simulation. And I'm aware that a lot of you guys maybe come from more diverse backgrounds. Some of you guys do quantum, and maybe some of you guys don't, but certainly you guys have a math background. So I'll speak a tiny little bit about both ordinary and partial differential equations, and I'll speak a little bit about quantum simulation a bit more generally, because the techniques that we're going to use is not just on qubit-based devices, like we can, but not exclusively on qubit-based devices, but also on continuous variable and analog devices as well. Oh, let me see. Right. So you guys know about ordinary and partial differential equations, since most of you guys who have, at least from a physics background, and even those of you guys who took physics in high school, right, for those in computer science who didn't do physics in university, you certainly would have seen ordinary and partial differential equations, because that's the essence of equations in physics. Like Newton's laws, right, they're essentially systems of ordinary differential equations. And things like fluid dynamics, Boltzmann's equations, and later on we might even see equations dominating in economics. Right, so, but certainly in the physical world, and if you care about things like cosmology and things like that, like quantum field theory, you can really write a lot of the key physical equations in the form, right, of partial differential equations. So they govern our world, and that they govern our world on multiple time and spatial scales. So things like fluid dynamics, the sort of macro scale, and the time scale is also not very small. But as you start going on to the more smaller scales, then you start hitting, say things like kinetic theory. So you care about, and then further down, molecular dynamics. So you would care about things like the actual molecules colliding with each other that make up the physics behind fluid dynamics. And of course, if we go further down, we hit quantum mechanics. So, and of course, the dominant equation for that is Schrodinger's equation. And it's a major problem in both mathematics as well as physics on how to actually slide up and down this scale. So, because we know Schrodinger's equation very well, and we know molecular dynamical equations very well, but what is the actual gap between quantum mechanics and something that is semi-classical and finally fully classical? So the classical and quantum divide, again, is still very much an open problem. So both in mathematics in a strict way, as well as physics. So how do you take the h bar going to zero? Sometimes it's not clear how to do that. So these things are mysteries. So our question is, what do we mean by quantum simulation of ordinary partial differential equations, which is not quantum mechanical in origin, meaning that we go further up the scale in terms of time and space? Well, there are a lot of ways of answering that. Because by looking at this kind of diagram, we know that essentially all the PDEs that we care about, all the ODEs and PDEs we care about, is mostly quantum mechanical. So you and I, right, the PDEs that govern us, we obey Schrodinger's equations. So in essence, all the classical simulations are already quantum mechanical simulations, right? So then So certainly it is possible, right, for quantum mechanics to simulate classical physics. So the question is not whether or not it is possible. Our question is whether or not it can be efficiently done. So if we want to model, right, all the, say, the molecules in an atom, right, that make up a fluid, if we really want to do that, then it's actually not going to be efficient even on a quantum device. So if we want to do it more efficiently, then we need to think of a different mapping, right, from the global macro classical mechanics, if these are the PDEs we want to solve, like into a quantum, into a Schrodinger type equation. So the thing is, we know it's possible, but we really want a different formulation, right, where even the quantum mechanical way of simulating it can be efficient. And we'll come back to this question. I mean, the reason I stop on this slide a little bit more is that later on, for us who will care about more foundational questions, so maybe the mapping that I talk about might have implications there as well. All right, so now I talk about ODEs and PDEs, what are they exactly? And just as a reminder, so ODEs, ordinary differential equations, are very different from partial differential equations. So if you say mathematically a system of ordinary differential equations, you have derivative with respect to one parameter, and usually an interesting one is, say, time, say for Newton's equations, and that govern things like molecular dynamics, particle swarm, birds flying in the sky, the pattern, electrical networks, etc. But whereas partial differential equations, the variable would depend on more than one parameter. So things like in fluid dynamics, financial market behavior, even in machine learning, very high dimensional PDEs. And even though PDEs, they have derivative with respect to just one more, or at least just one more parameter, they're very, very different because a single PDE, even if it has one extra parameter than the ODE, say one-dimensional in space, it really corresponds to an infinite number of ODEs. So the complexity in simulating them becomes very, very different. And our question is, can we put them on quantum hardware? And as we said before, it's always possible to put on quantum hardware because it's already in quantum hardware. Everything we know of is quantum mechanical. But we want to do it in such a way that we don't have this curse of dimensionality. So we know that if we want to simulate very high dimensional PDEs, and again, a single PDE is really an infinite number of ODEs, then if you have a d-dimensional PDE, then actually a lot of the numerical methods, they scale exponentially with that dimension. So now if you want to put that on a quantum device, then, and if you want to get to the basic quantum mechanics behind the classical dynamics, then you're really still going to get a very, very high dimensional problem. So quantum mechanics is not going to help with that. So we want to find a mapping where instead of mapping to a very, very high dimensional quantum mechanical system, we want to map to a quantum mechanical system that is not much higher than d dimensions. Okay, and in fact, we'll show that if we want to do a mapping of a linear PDE to another linear PDE, then at most, if it's a homogeneous problem, we add in just one more dimension. And then if you start having inhomogeneous problems, then we just add another dimension. But we'll talk about this later. How to map a non-Schrodinger type of equation, say governing classical mechanics, into a Schrodinger type equation. And a name we chose for that is Schrodingerization. And it came out just because this is the way that we talked about it as we were working on it. And then when it came to writing the paper, it's like, let's just use the name that we've been using all along. So, right, so we'll introduce this method later on. And essentially the key is how do you map the classical dynamics into a quantum mechanical problem that just one more dimension higher, okay, than the original problem.
And a quick question on this. What is the meaning of efficient in this case? Quantum mechanical modeling efficient, is it in terms of resources or time?
Yeah, so very good question. It's actually what I'm going to say on this slide. There are many very good. Yes, good question. So yeah, so what's the point of going beyond the classical infrastructure? We can care about time, we can care about memory, we can care about energy, communication, all of that. And the particular ones that we're interested in right now is time efficiency. So when we think about numerical methods on classical devices, and again, a lot of the bottleneck indeed is time, but also there are savings in terms of memory as well, that if we had access to quantum memory that is very reliable and is very good, it would also save on memory as well. And it will be efficient in terms of the dimension of the problem. And I'll show you some numbers a bit later on, but just to get basic idea. Right, so when I say Schrodinger's equation, what do I mean? So this is a linear differential equation. And there are actually two forms. There's an ordinary differential equation form and a partial differential equation form. But basically the key physics or the key quantity that is involved to talk about Schrodinger's equation is something we call a Hamiltonian. So this is this H quantity there. And you can think about this as an operator that tells you about the energy of the system. So all the particular dynamics that's involved in Schrodinger's equations is captured purely by this Hamiltonian. And it's something called a Hermitian operator. And because H is Hermitian, then the evolution of the quantum state obeys something called unitary dynamics. And by unitary, it means you can go back and forth, so it's reversible. Right? And the key message out of all of this in this talk is that not just the computational techniques, but also the mathematical language that we must use if we change up the infrastructure from classical to quantum, that itself must change. And especially for those of you who come from computer science, it will be a particularly big message for you guys because computer science, as you've learned it, because all you guys are too young, that you were born into the age of people only working with bits, 0 and 1. Indeed, all computer science is born out of that from Turing. But in fact, we can see that information can be encoded in other ways, and I'll talk about that a bit later. Right, so what do we mean by quantum simulation? So we mean that if we start off with an actual quantum system, and by that, of course, like I said, all of us are quantum, but I mean capturing fully the quantum mechanical behavior. So we're you and I, even though we're quantum, but we can also be described in a purely classical way, mostly. So if you're looking at a quantum system and you have all the quantum characteristics that's captured in there, so that's the quantum state that we mean, we want to ask, after a certain amount of time, say t, what is this quantum state? And as we said before, this evolution, if we obey Schrodinger's equation, and again, we're not introducing noise in here, so non-noisy system obeys Schrodinger's equation and evolves by unitary dynamics. Again, without noise, you can go back and forth. And if we want to simulate, say, an n two-level systems and one two-level system, quantum two-level system, we call a quantum bit or a qubit. On a classical device, even just to have this memory, right, you need 2 to the power of n entries, which is, as n is very high, this gets expensive pretty quickly in terms of memory. But if you want to also simulate the evolution, you imagine that you're multiplying this very large matrix by multiplying this large vector by a very large matrix now, this U as a matrix. And if you're doing matrix multiplication, that gets, again, exponentially expensive, right? If you have a 2 to the power of n by 2 to the power of n matrix. But whereas if you want to simulate this on a quantum device itself, if your system was already quantum, then you don't need 2 to the power of n entries in terms of classical memory, but in terms of quantum memory, you need just n, okay, qubits, quantum bits. And then the evolution, right, of this quantum system, just the evolution of this n bits. Now, n qubits. So already we're reaching the limit of what classical computers can easily simulate. So now we have hundreds, okay, of quantum qubits, which, I mean, we do actually have many more than that. All of us are actually many more than that, but I do mean clean qubits, not noisy ones. And if we want to simulate continuous variable systems, and I'll explain what those are, then actually we can get up to millions of these modes. As we're already reaching beyond the limit of what classical computers can easily simulate, both in terms of memory as well as time, meaning we can think about it as multiplying by this large matrix as it evolves. So again, quantum simulations are very effective at simulating quantum systems. So if we have a classical system, for example, that obeys classical equations, if there's a way of mapping that onto a quantum system whose dimension is not too high, then we can actually capture, right, this ability of quantum devices to simulate quantum devices without this cursor dimensionality. So this is the idea why we care about doing this Schrodingerization, meaning making something non-Schrodinger into Schrodinger, so we can take advantage of quantum simulation. All right, so for those of you who sort of probably haven't seen quantum bits before, or qubits, for those in computer science, you guys are very familiar with bits, 0 and 1. Now when we think about 0 and 1, because usually a lot of the systems that we care about, or that we can see in the classical world, they can embed information that is binary, either one or the other, like black and white, transistor on and off, and of course the Turing model, you have a hole punched or not a hole punched. But if you have quantum mechanical systems, actually can embed information that's not just binary 0, 1, it can actually be a lot richer, right? And I feel that the best way to think about this is actually probably on a mathematical level. I use a block sphere, but then it gets tricky if we go to high dimensions. So maybe it's best to think about if we're encoding, say, information in terms of the energy level, either if it's a ground state, okay, lowest energy level, you can say it's 0. The second, the highest level energy, that's say 1, so you can say it's either 0 or 1, that's a bit, right? However, quantum states, they can capture, I mean, people say states in between, but it's actually more than that. So I think it's best to say this in an abstract way, that quantum states can be represented by a complex valued vector, right? That spans 0, 1, the ground state or first excited state, but it can be any arrow, right? That points in between, in such a way that the length of this arrow, right? And by length, I mean captured by alpha squared plus beta squared, that's always 1. So, and it's really important to say this alpha and beta, they're complex valued. If they're only real valued, then that makes sense to say it's a mixture of 0 and 1. And the mixture in the same way we mean classically, but it's really important that this is complex, because if it's complex valued, then we actually have this interference phenomenon happening. And you might have heard about this in some previous lectures. Right, so then if we have n qubits, then this is 2 to the power of n dimensional space, and then we have Pauli operators that you probably have seen before in your previous lectures, and again, this acts on n, okay, of these qubit systems, and each one of these you can think about as a vector, n0, 1, but of course in a high dimensional space, then you think about a very large dimensional vector with complex entries. So this is digital quantum information. And if we care about the evolution of this, then you really think about a matrix language. How do you get from one vector to another vector? And the evolution is by unitary evolution. Everything here is linear. And of course, everything linear we can describe using this matrix language for this finite dimensional space. And of course, the time evolution, usually the way that it's explained is actually through digital evolution. So bits, that's something discrete, but actually evolution, that can also happen in a discrete way. It's not the only way, but usually this is how quantum simulation is described. I'll describe later that we will not always need to use this. So time evolution through concatenation of a large number of gates. So you would have seen talks before on you have a universal gate set. It's kind of like Lego pieces, right? If you want to make any Lego model that you want, you're given some primary pieces, maybe ones of different colors, some different sizes, and this is a set number or type of types. And if you have those, then you can build kind of whatever you want. And this is the same idea. You have universal gate set, these basic Lego pieces, and you want to construct any unitary that you want from this set. As an example, you probably might have heard about Trotter decomposition. That's one way of doing it. And really for these ones, when you need a lot of these Lego blocks, you need something called a fault-tolerant digital quantum simulator. And you can imagine, just like when you're building Lego pieces, imagine coming from the factory, every single one of these Lego pieces is a little bit crooked. So of course, if you want to build a very large model, then a little error is going to get worse and worse until you really can't build, say, like an Eiffel Tower from your Lego pieces. Each one of them, right, has something wrong with it. And this is the same idea in quantum. The error is going to propagate. And then, so what we're going to talk about later, is something that is not a digital language in terms of both space as well as time. And here this is a time, okay, digital in time. And so in continuous in space is what we call analog quantum information. And the mathematical language you use for that is also different. It's no longer matrix language. It's what we call operator language. And usually people who do quantum information, they don't use this so much. And some people in computer science haven't even heard about this at all, right? And it's a little bit strange to me, because everything we know of in reality is all continuous variable, unless you go into the quantum gravity limit and you're quantizing gravity or something in space and time. Space and time, as far as we know, at the scales that we care about, at least, are continuous. And we call, and in fact, in your first lessons in quantum mechanics, right, you would hear about, instead of qubits, if you're a physicist, you would hear about wave functions. And a wave function has information that tell you the probability of you observing, right, your state in a particular region in space. And of course, a wave function is continuous. So So a continuous version of a quantum bit is what we call a quantum mode, or Qmode for short. So sometimes called continuous variable quantum state, sometimes Qmode, but I'll use the word Qmode for short. So instead of quantum bit, quantum mode. And here you can think that if your digital quantum state, U, is a sum, right, over the basis states, say 0, 1, and later like 2, 3, 4, etc. If you have high dimensional state, here your x is continuous. And of course, as we summation, the summation sign, if it goes to continuous limit, that just becomes an integral. So then this notation should make sense from that perspective. And the amplitude, so this is like the equivalent of alpha and beta previously, but now it's a function of this real value, x. This u of x is what we commonly call wave function. So this is something that is actually very, very familiar, but somehow put into the quantum information context, a Qmode is somehow less, people don't hear about it as much. But just think, it's actually the most natural thing. And so now, but if we care about the evolution, right, of Qmode, then this is really an infinite dimensional system, right? Because x, right, it's a real valued system, right? So, and then each of this x ket is a member of this basis state, right, of the basis that goes across, or that spans this whole infinite dimensional system. So then if we care about the evolution of this infinite dimensional vectors, we don't really use matrices anymore. Well, we have these infinite dimensional matrices, but we call them operators instead. And the major operators, that we care about, in this setting, are things like x hat and p hat. And this is what we call, space and momentum operators. And again, this should be very familiar from the classical context. And indeed, these are kind of like the quantum versions of space and momentum, very roughly speaking. And indeed, one of the key observations at the beginning of quantum mechanics is actually if you quantize, right, if space x, position and momentum p becomes quantized, then actually the operators x hat and p hat don't commute. And this gives you the famous Heisenberg uncertainty principle. It's based exactly on the fact that x hat and p hat don't commute in the quantum mechanical context. And one way of seeing the fact that they don't commute is that actually if you apply, right, the x hat onto your Qmode u, then this is actually equivalent, right, to just multiplying the wave function by x. But actually, if you do I times p hat, momentum operator on u, in fact, you get a derivative of u. And as we know, x and the derivative with respect to x, these are they don't commute with each other. You can check they actually obey the same commutation relation as x hat and p hat. And another thing that's quite important for us later on is that actually the inner product between x and p, they actually give you e to the minus ixp. And if you guys see this, where else have you seen e to the power of ixp before? So that's something that you would learn about in first or second year math, which is doing Fourier transforms or continuous Fourier transforms. So in fact, if you do a Fourier transform on x, that actually gives you p. So you would have heard about in previous lectures that actually quantum Fourier transforms, and actually when you hear about it before, it's in the context of digital quantum Fourier transforms. These are really the backbone of a lot of the major quantum algorithms that are out there. And it's very expensive if you want to do it with qubits. But as you see in this context, actually doing Fourier transform is really just changing a basis from position to momentum. It's actually super easy. And actually, if you use optical systems, it's actually even easier to do this. So already that we see that there are some operations, like quantum Fourier transforms, which are more natural to do in this continuous language rather than digital. And this will be very important for us later when we're dealing with partial differential equations, which, as we know, are continuous in nature. So just something to remember. So if we have x hat, we can think about this as x multiplied by the wave function, and ip hat can be replaced by taking a derivative with respect to u. So we'll use this a lot later. And
sorry, hi Dana. Can we take a bit of some of the questions?
Yeah, absolutely. Yeah.
Awesome. Kind of starting from the previous slide, is this somehow related to the second quantization?
Oh, sorry. Is this related to quantization? Is that the question?
Yeah.
Oh yeah, so it depends on first or second quantization. These are actually very different things. But usually when people, like in classes, usually in physics, when you motivate quantum mechanical equations, then you say, well, we know what position momentum are classically. And we want to show why in quantum mechanics is actually so different to classical mechanics. So, and then what you do is that you promote a scalar quantity like x and p to an operator. And you can show that we know that classically position momentum, they do commute with each other, like space and speed. You can measure two kind of at the same time with exactly precisely, both of them. But if you promote them to operators, because they don't commute, it means they don't share eigenvectors, which means you cannot know their absolute value at the same time. So this is what we call first quantization, when you put little x's, when you put little hats on x and p. So in that sense, what I talked about here is related to quantization. Yes.
Awesome. Thank you. And another question, can analog quantum systems also be simulated through these digital circuits? Like if there are more than two-level systems?
Can a CV system simulate Qubits? Yes, yes. I will talk about. Well, so this I will talk about this later on. We'll come back to this point, but I think we have to distinguish between two things. One is if we're able to do the approximation. So if we have very, very high dimensional qubits, they're essentially CV systems. And then you have to work out errors, how well they're able to simulate them. But on the other hand, say, well, maybe if there are problems that we can use qubits or we can use CV. And then I'll talk about that later as well. And then another interpretation of this question is if you already have CV systems, can you actually use these to also simulate digital systems? And that's, again, a yes, because that's essentially every system that we have, every quantum mechanical system, every company and every university that claims they have a quantum computer, these are all CV systems without exception. But what they do, like in order for them to use these to simulate digital systems, is that they have to, let's say if you want to use superconducting systems, I mean, essentially these are anharmonic oscillators. And then you're cutting off the higher levels. So then you only have, say, 0, 1. Of course, if you're able to control a higher level, then you can have qubits as well, not just qubits. That's the question. And of course, for different systems, you can access lower or higher levels. And I'll talk about those a bit later when we come to Rydberg atoms. So yeah, so I hope that covers the different interpretations of that question. But we will come to those points later as well.
Thank you. Another maybe a basic question, like can you explain a little bit on what do you mean by fault tolerance and why is it significant?
Oh, well, that's a huge question, which I can't, and actually, I don't know if this is a good point, I mean, Ayad, for you to advertise talks later where you do. I'll answer in a super, super short way, super, super short, which is like the Lego thing I was talking about, right? So each of these little universal gates, each of these pieces that you use, when each of them have errors, right, you can imagine that someone comes in to correct each of these errors. They shave down like an extra little bump that you might have on a Lego piece. But you scraping that little bump, that's going to cost you effort. So if you want to say what is the total effort in building up this big Lego piece, right, you have to include the extra labor cost in you shaving down the fact that each of these Lego pieces haven't been built properly. And this is the same in quantum computers. You have what are called error correction schemes. And to correct for each error that comes up, you need to actually use up more qubits and operations to correct for these errors. So, and it could be that actually the effort that you use is actually more than the cost it takes for you to do the computation if it was done perfectly. So then it would not be good use of your device. It would actually cost you more effort to do that. So fault tolerance means that actually if you also include the effort to correct for these errors, that when you add up the total, it doesn't cost you more. So then it's actually worth you doing this quantum computation in the first place. So this is the super quick answer.
Thank you. I'll just take one more question. What's more powerful than qubits?
Sorry, what was the question?
Are qmodes more powerful than qubits?
I will talk about that in the next slide. I call the power one Qumode. Yes, I'll talk about this in just the next slide. Oh, sorry, in just a few more slides. Yeah, a taste of how powerful Qmodes can be. Yeah, we'll get to that in just a bit.
Awesome. Yeah, thank you. Keep going.
Awesome. So actually, I just realized I'm going a little bit slower than I anticipated. So there will be details later that I might skip, but you're free to ask questions later, and I can send materials over for those of you who are more interested in details. All right. So before, when I talked about digital language, okay, meaning matrices and finite dimensional vectors, we talked about qubits and the fact that they evolve in a digital way. Now, when it comes to continuous systems, we talk about continuous variable quantum systems modes, but actually the evolution itself, and then we use the evolution itself can also be captured in a continuous way, because we know that the natural dynamics of quantum systems, that happens in continuous time, right? At least at the scale that we care about. I don't mean quantum gravity scale. So time as we in the scale that we care about is a continuous quantity. Yeah, so if you're able to design, or if you have a quantum system, whose natural Hamiltonian, okay, that we care about, and Hamiltonian again, it captures everything, okay, that you need to know about your quantum mechanical system that obeys Schrodinger's equation. If it evolves naturally with time, then we don't need these gates. We don't need all these Lego pieces, because you can think about the equivalent, I like to think about as Play-Doh. So Lego means that you have a set number of pieces and you want to build up to whatever you want. But a Play-Doh, right? Someone gives you a piece of Play-Doh and you can mold it to however you like in a continuous way, right? So analog quantum simulation is when you have evolution in continuous time, and you can have that as well, without breaking it up into lots of gates. So we have these possibilities. And all of these things that I talked about, I feel can be captured very nicely in this diagram. So everything here is quantum simulation. And on the top, we have data encoding. So this is like digital continuous in space. So we have like qubits, modes, we already seen that. But the data processing, okay, meaning the evolution that we care about, can also be digital or continuous. And in the discrete side, and this, if you use qubits and it's discrete, this is called circuit model quantum computing, and actually almost all the quantum algorithms that you might hear about is of this type. Almost all the quantum algorithms lectures that you might hear about for fault-tolerant setting. Circuit-based model. Some of you might have heard of measurement-based quantum computing, like it also, and again, it's the same order of complexity as circuit models. It's digital. But however, you can also have qubits, but the evolution itself is continuous. So some of you might have heard about adiabatic quantum computing or quantum walks and quantum annealing. So this is continuous time quantum computation, but using qubits. But if you use qumodes, we also have two types. So if you hear about continuous variable quantum computing, typically, not all the time, but typically, it means you're using qumodes. However, you can't engineer any kind of evolution that you want. So you also have these Lego pieces for continuous variable devices. So you also have these basic gate sets, and then you want to compose these gate sets in such a way that you can have any evolution of qumodes. However, if you have continuous on both sides, both data encoding as well as data processing, then you have quantum analog computing. And I love this very, very much, because this is how nature does it. So nature does it continuous in time way as well as continuous in space way. So in the algorithms that I'm going to talk about, in fact, we can realize them in all of these four corners. We can realize them with quantum analog computing. We can realize them with continuous variable quantum computing, circuit model quantum computing, adiabatic kind of as well. So we can realize them with all of these kinds. But I will concentrate mainly with the quantum analog computing language, because as we'll see, when we apply them to PDEs, it's actually most natural, because ODEs and PDEs, the ones that we want to solve, and again, they're continuous in itself in space and time. So I feel this to be the most easy in terms of learning the techniques, and then we can always discretize space on time as you like to fit these other methods. All right, so now we had the question before, how powerful qumodes are. And I will actually, before I talk about Shor's algorithm, before I talk about this, let me just mention something about classical analog versus digital. Now, for those of you who do classical computing, you would know very well about the Turing model and how powerful the Turing model can be, and everything that we compare it to, like including when we use a lot of quantum computing, computer scientists use this as a way of proving or disproving the Church-Turing thesis. Meaning, if we add qubits, can it be more powerful than the Turing model? But all of these, they're in the basic digital language, actually. So if we have continuous variables, even in the classical way, then we no longer have the Turing model. So forget even qumodes, just think about classical continuous variables. If we had devices made from classical continuous variables, and we do have these devices, they're called classical analog devices, except classical people just call it analog, okay, devices, then if you actually don't have errors in them, there's something called the BSS model for classical computing, but using classical continuous variables, it's actually much more powerful than the Turing machine. So if you don't have errors, right, it can completely, they're very, very powerful. So of course, if you have perfect Qmodes as well, then it's even more powerful potentially. Then, however, if in the classical world, if you introduce errors into your classical continuous variables, then you cannot get better than the Turing model. And similarly, well, it hasn't been proved in the quantum case. So again, this is an open question. If you have quantum modes, if you have errors, how powerful is that compared to quantum devices? So this is from a basic computer science model, like this is an open question. We don't know that. But certainly it's at least as powerful. But we don't know if it's going to be much more powerful or not. But when I say power here, I don't only mean in a computer science sense, as we'll see. So it also refers to implementability. Yeah, so there are lots of ways of interpreting power in this case. So you guys all know about Shor's algorithm. So if you want to classically break this, it's very expensive, but quantumly, and again, these numbers, I think they're probably improved now. If you have a lot of perfect qubits, but for noisy systems, you need even more physical qubits. But certainly, the idea is that you need a lot of qubits. But as we saw before, one qmode really is an infinite dimensional vector in Hilbert space. So in principle, a single qmode, right, can really capture a whole lot of qubits. And it's actually, I won't show you the full mathematics. You can actually, I don't have the references. I actually don't have a lot of references here in this paper, but if you want, in these slides, but if you want to ask me for references later, you can. I can show you where they are. So I had a paper many years ago called the Power One Qmode. So that was one of the audience talks. So, and you can actually show that you can replace all the important qubits, like in Shor's algorithm, by a single qmode. And actually the power of this qmode is actually defined by something called the squeezing level of this qmode. So if you have a laser light, so this is the wave function of this is something called a Gaussian state. But by squeezing it, it means that this Gaussian becomes more and more and more thin. So it becomes closer and closer to, say, a position eigenstate. So you say the position, the quadrature of the state more and more. So and the higher the squeezing actually would correspond you to being able to replace this by more and more qubits. So in this case, you can just use a single qubit instead of, you can use a single qmode instead of all these other qmodes, like over 4,000 qmodes, to actually simulate Shor's algorithm. So this is, yeah. And you can also do things like trying to find the trace of large matrices and so on. But of course, actually, to get this high level squeezing is actually very, very difficult. So it's not. Now we go to the question, what about the quantum simulation of classical ODEs or PDEs? So again, I just want to put these things side to side. So what we want to do is that we want to have either a system of d-dimensional ODEs or a little d plus 1 dimensional PD, and these kinds. How do we map them onto equations of Schrodinger's form? And again, to say an ODE is really, you have a variable that is a derivative with respect to one parameter, time, whereas with PD, you can have derivatives with respect to multiple parameters. But what do we mean by mapping onto equation of Schrodinger's form? Well, Schrodinger's form actually has two types. It can be written in the ODE type as well as the PDE type. Now, usually if we think about a system of if we have two-level systems, like n two-level systems we had before, and qubits, then we know the evolution is with respect to a unitary operation. So you can describe things in terms of matrices. So the state that you have is now a finite dimensional vector, and the evolution is by a matrix. So if it's d-dimensional, so then this Schrodinger's equation is a system of d ordinary differential equations, and it's usually coupled. So, and d here would be a d by d Hermitian matrix. However, if we talk about the evolution of a wave function, we know a wave function is continuous, then you can describe it in terms of a PD. And for physicists, right-hand side, the PD form is the way that we've actually been introduced to Schrodinger's equation. So you see that we have like this Laplacian operator, and we have a V. And this V is the potential. And remember when I said H is really talking about the energy of the system? And in this first quantization interpretation, then your Hamiltonian, even though it's an operator now, is still think about as describing the energy of the system. And energy, as we know classically, has a kinetic part and a potential part. And if you do the first quantization, then Hamiltonian also has a kinetic, corresponding kinetic, as well as potential part. So V of x, so that is the potential energy part. And if you look at a Laplacian is essentially second derivative with respect to your spatial dimension. And remember, we had slides before that whenever you see IP hat, that's really a derivative with respect to your spatial dimension. So then minus the Laplacian factor is essentially a p hat squared operator. And we know that classically, the kinetic energy is essentially scales like momentum squared. So hopefully this gives you an intuitive kind of picture why Schrodinger equation has this form. Now, on the ODE side, your Hamiltonian is a d by d Hermitian matrix. Just remember digital, that's using the matrix language. But now in the continuous variable, the analog form as well, Hamiltonian is now an operator. So these are infinite dimensional matrices. We call them operators, but it's still Hermitian. So now, and if we go back, what our question is, whenever we have classical ODEs on the form on the left-hand side, we want to map to system of DODs on the Schrodinger side, on the left-hand side. And then if we go back again, if we have classical D plus one dimensional PDEs and plus one just means time here, PDEs, we want to map onto the right-hand side of Schrodinger's form. And of course, the Hamiltonian sometimes has this momentum form, but there are ways of actually getting rid of this momentum form as well. So, but we do want a Hermitian operator. That's the key. So, and just a basic summary of what we want to see later on. So with classical and quantum devices, we both have digital as well as analog devices, as we saw before. Now, classically, if you want to solve a lot of the, actually all of the numerical methods are developed for PDEs that you guys learn about in math, and that what we use on today's supercomputers, and as well as non-supercomputers. A lot of the methods have the cursor dimensionality. There are methods like Monte Carlo, right? So which don't have the cursor dimensionality. However, they do have an issue where some of the variance can be very high. So a lot of the reliable methods for solving PDEs, they really do have the cursor dimensionality, meaning the time cost, right, scales exponentially with the dimension. Now, we also do have classical analog devices. And actually, in the history of computing, the first devices we had were analog devices. And those are the first ones were actually to solve differential equations, actually. But all of you guys are too young to know about those. Yeah, so however, they're really very good for solving ODEs. However, as I mentioned before, a single PDE is really an infinite number of ODEs. So if you really want to use analog classical devices to solve PDEs, then actually you will need to discretize your PDE. So you have many ODEs, and then you solve them on parallel analog classical devices. But still, you have to deal with discretization. So both classical analog and digital analog for solving PDEs, I mean, one has a problem with cursor dimensionality, but also you have to discretize them. But now let's talk at the quantum side. So a lot of what you hear about, and actually for later talks, for quantum algorithms for differential equations, partial differential equations, they actually also rely on digitizing PDEs. So you no longer have the continuous form of your PDE, so nice derivatives with respect to time and space. And in particular in space, you discretize those. So, and all of your classical numerical methods are based on these. And then you map them into the qubit dynamics. And again, if you have nice properties, okay, there are subtleties related to these, but what you hope, like the best, is that you have a quantum cost that is now polynomial in dimension and logarithmic in n, which is the discretization size. So if you have x, how many little pieces, okay, do you chop this x up into? And of course, the higher the n, the better your precision. So you better hope that your method is logarithmic in this n, instead of scaling very highly with n. So, but then we also have analog quantum, right? And here, and this is a method that we will propose, right? Where your PD can be mapped directly onto the continuous quantum system in a way that keeps the continuity in both space as well as time, right? And here, no discretization is necessary at all because you automatically use your continuous quantum system. And your quantum cost is actually linear in the dimension. And the method that I'll talk about, Schrodingerization, it works on both analog quantum, and you can also work on analog. It can also work on quantum digital as well. But the important thing to note here, and I will mention this again later, is that actually entanglement plays a really nice role in this, that it allows us to be able to keep the continuity in space, whereas we won't be able to do this on classical analog devices generally, because we don't have access to entanglement. And so before, when we had the question of what efficient means, so this is, yeah, gives you a basic idea of what I mean, okay, by efficient. Linear, or at least polynomial in dimension, and either logarithmic in discretization size, or no discretization at all. So, and now we're back to this slide, and I would like to do a little poll here, Katie, if that's like we discussed earlier. So now there are lots of different kinds of ODEs and PDEs. Now the most straightforward one, which I'll start with, are linear PDEs. And this means that this function of f, capital F, both on the ODE side and PDE side, you see in the blue and orange boxes, they're both linear functions of x and u, and the derivatives of u. But we can also have cases where the coefficients that's involved in these functions of f, they either depend on time or don't depend on time. So, and the ones that also depend on time, they're called non-autonomous systems. And actually, if you want to simulate those in a quantum way, if you want to simulate, say, time-dependent Hamiltonians, then there are more sophisticated methods for those. So in part 2 of this is actually dedicated to non-autonomous systems. And you can also have cases where, say, the coefficients of your ODs or PDs, you actually don't really know what they are precisely. You might know the probability distribution behind these coefficients, but you don't know what they are. So are there efficient ways of solving those? So that is part 3 of this talk. And the last part, part 4, is nonlinear PDs. So Katie, if I could have a poll of which ones people are more interested in. Part 1, I definitely have to talk about. But for the other parts, if I can have, yeah, if you vote for which one you like most, and then I'll go to that one first, because I also understand we have a time issue, and I took longer than I expected.
Right, I've just posted that. So everyone, it is in the live questions chat. So please start answering the poll.
Maybe we can take a few questions as people answer the poll. Awesome. What kind of errors in Qmode computing?
Oh, very good. So actually, again, Qmodes computing comes in 2 kinds. So let me go here. So we can do them in digital way, the digital processing way, like in continuous variable quantum computing. And this becomes very difficult. Like it would meet the same kind of problems as you do with digital quantum simulation with qubits, because again, you have these universal gates, but each of these gates would have a little bit of error associated with them, and you need fault tolerant continuous variable quantum computing. So these are things, yeah. However, when it comes to analog quantum computing, that's a very, very different story. So in this case, you essentially have one gate, because here you're saying you have a quantum system that naturally realizes this evolution. You only need to stop it once your time stops. So then it becomes about estimating the error in doing this natural evolution. But this is one gate. And the error associated with that would really very much depend on your system. And how well you can control it is really how well you can do the quantum control. So it's, yeah, of your system. So, but it will be very different in nature compared to if you were to simulate using digital kits. But again, with Qumodes, you can have both the digital quantum simulation or analog quantum simulation. Yeah, but in terms of what we'll talk about in here, I'll focus mostly on the quantum analog simulation, where essentially you just have one gate.
Thank you. Maybe you have time for one more question?
Yeah.
Okay, I'll go off one more question. Could a single or a pair of Qmodes implement universal quantum computing?
Yeah, so this is actually, this is a very good question. I mean, in principle, if you can reuse the Qmodes, then yes. So yeah, if you can reuse them. But something also that I want to, like, since we have this question, I do want to say something about Because I know that a lot in computer science, what people care about is just to minimize the complexity. Can we just use one Qmode? Can we just use one gate? Or like just minimize time and so on. But there's another really important thing when it comes to algorithms, which is the simplicity of implementation. So, for example, in a world where we're not missing Qmodes, like before I said, actually in the lab, we can have access to 1 million Qmodes. Actually, we actually have some experiments running. We have tens of thousands, right, of Qmodes. So in an era where we're not missing that, then we really want to use as many as we have kind of available, but to make the actual algorithm simple. So even though something may be possible, it may not be the choice that we wanted to make, right? In order for the process to be simple. Yeah, and this is also the I guess a lot in computer science, we care about lowering complexity. A lot of the time, if you care about asymptotic scaling and you want to get a better polynomial factor or whatever, but usually the complexity, like in terms of the complications, I don't want to say complexity to confuse with the scaling, but the complications involved in your algorithm, it can actually go up very quickly. So it becomes very hard to program and you don't really see what's going on. So what we want to aim for in terms of our quantum algorithms is that really care about simplicity, not just about lowering resources, but really about the simplicity, not just of the algorithm, but also of the implementation as much as possible. So we'll keep this in mind because it will actually also be important. Yeah.
Yeah.
So
I hadn't considered that. That's great.
So the voting is now in, and part 4 has won with 51% of the votes.
Okay, all right. So we'll go straight there after linear. So I'll first talk about, I can't escape doing linear ones. So I'll first introduce the method that we have, and this is about turning all nonlinear non-Schrodinger's equations into ones of Schrodinger's type. And by Schrodinger's, I mean this linear Schrodinger's equation that we have. So, and let's have a look at the simplest equation. So, and here we have first derivative with respect to t, and then is equal to L, where L is a linear operator. And we have two examples here. One, we have Schrodinger's equation. So L is minus I, and we have this Laplacian plus the momentum. And remember here, we have the potential, V of x. And here it should remind you of the kinetic energy part, the p squared part, plus the potential energy part. And let's have a look at the heat equation with a forcing term. And again, if the L linear operator, it's also a linear operator, but now it's instead of minus I, it's just minus. So now if we look at these two equations, actually the physics is very, very, very different. One is quantum mechanics, and the other one is the heat equation. So, but what do we notice about them? Right? Like they're basically the same, right? Except an I. And then you're like, oh, it's like so close, right? It's almost there, right? So let's just try and get rid of an I. How hard can that be, right? And that's what people said. How hard can that be, right? So because it's an I, right? So you try and move I from one side to the other. And this is kind of, so this is a method, what some people call the quantum imaginary time evolution method. And in physics, it's called the Wick rotation. And this is actually also a way people try and understand statistical mechanics from this, like for those of you with thermal state, e to the minus beta h. If you do a Wick rotation, the beta goes to I beta, and you can think about this in a quantum mechanical sense. But anyhow, that's the point is, how hard is it to get rid of an I? It's t goes to it. It's like, oh, we're done, right? We're done. However, this imaginary time evolution, and by that I mean t going to it transformation, it does not give you the solution to the heat equation in time t, right? It's actually a very complicated procedure. And yeah, so if you actually do this e to the minus it, actually the mapping, it doesn't give you the same Hamiltonian. So actually what you need to do is that you need to evolve for a little bit, right? You need to do a bit of tomography on your system to find out the next step, the next Hamiltonian you need to apply in order to do this t to the it mapping. So it's actually not straightforward at all, even though mathematically it looks like you can just do that. So, but what we would like is that we want to simulate Schrodinger's equation in time t so that it would actually give us back the solution of the heat equation in time t. That's what we want. So then we want a real-time way to Schrodingerize the heat equation to gain this extra I. So without making t imaginary, to get an extra I back. That's the basic mathematical question. And now to think, well, how do we get this extra I? How do we do that? Well, so I will explain, I will go through like the mathematics of this, and I'll kind of motivate this as well. So before we go through the math bit by bit, let's think about how you get an I in front of things. Well, what's another way of getting I's without changing the equation too much? Well, one is about changing the representation. So we know that we can have a function, or we can have its Fourier transform, but the information that's contained in there doesn't really change. And a Fourier transform, like we know, has this e to the I xp on the side. And you're like, oh, well, we have e to the I xp, so I is actually at the front, so it's in the exponential, but we really want an I at the front. So how do we get an I at the front if we have a Fourier transform of a state of a function? Right? Well, you see, well, if you have an e to the I xp, right? One way of getting I out to the front instead of in the exponent is really to differentiate it, right? But then you say, well, if we differentiate it, then we've actually changed our function, right? By changing a function to its Fourier transform, we don't change the information. But if we take a derivative, we've changed the information in there. But then you say, hey, well, what about a case where if we take a derivative or something, it's actually proportional to itself, so we don't actually change the information, right? What kind of function is that? Well, that's the exponential function. So that's e to the minus I. So if you have an exponential function and you take its derivative, it's proportional to itself. So that provides a basic motivation why we actually want a function like e to the minus psi, an exponential function, because by then taking a derivative with Fourier transform, we actually get an I out at the front without actually changing the function very much. So just keep this in mind as we go, and I'll go through the actual derivation. So the trick is here is that we add one extra spatial dimension, psi, and we apply something that is we call the warped phase transformation. This was inspired by, because I used to do high energy physics, and I worked on models like random sundry models where actually the universe has an extra dimension and gravity leaks into this extra dimension, because it's a way of explaining why gravity is so much weaker than the other forces in our normal four-dimensional world. Yeah, and it leaks, and this leaking is exponentially, okay, leaking. So this is inspired by that. So we introduce an extra dimension psi, and u of t of x, so suppose that obeys the heat equation, but let's add this extra dimension, and we add an extra factor, e to the minus psi. And now if u obeys the heat equation, we ask what equation does w obey? And the w then obeys on the bottom the heat equation in phase space, so this extra psi adds an extra phase in quotation marks. And then we see that dw dt now you have this heat equation part, but instead you can rewrite it in terms of the first derivative, right, dw d psi. Because as we know, if we take a derivative with respect to psi, we get minus that function because it's derivative of an exponential function. And already now you can kind of see the trick, because if you take a Fourier transform of this w and then we take the derivative, that's how we get an extra I back. But before we do that, I just want to mention, if we now solve the equation with respect to w, right, how do we actually recover u? Well, this is very easy. So you can choose to take an integral between 0 and infinity. So you can show that. Or you can pick any psi that is larger than 0, and then divide it by e to the psi, where the psi is larger than 0. So you can also, if you solve this heat equation in phase space, you can easily recover your u. Now, we don't want to quite solve the equation just in w. We want to solve it in terms of w tilde. So if we take the Fourier transform in psi, then we have this relationship between w and w tilde with respect to Fourier transform. So now if we rewrite the heat equation phase space, now in terms of the Fourier transform of w tilde, now this is where we get an extra I, because now we're taking derivative of dw d psi, and because we have the factor e to the minus I psi eta, where eta is now the Fourier mode to psi. So these are kind of the XP pairs. And you're like, hey, we got an I now at the front like we needed, and now you can see why we needed the warped phase e to the minus psi why that's kind of the best function to use. And you're like, yay, we've solved our problem now. But now we, instead of t going to it, because now it's real, t goes to eta t, where eta is your Fourier mode. So now this is like a real number going from -infinity to infinity. And now you're like, well, here we've kind of now have an infinite number of Schrodinger's equations. That's what it looks like. But no need to fear, it still makes sense because now we can actually use Qmodes in this. Oh, and I just want to mention now the initial state that we have. It's really, now because it's doubly tilde, it's a Fourier transform of this e to the minus psi. So then we have this function here. So how to implement this and still in a way that makes sense when we have an infinite number of them, of etas. Well, so our trick to make this into the quantum state, our x goes to x hat, our eta goes to eta hat, and eta is, you can think about this as, say, x, but in another mode. So here, if this is, say, one-dimensional, then this is like a one laser beam, and then eta is actually the position of like another laser beam. So this is what we mean by mode. Like one mode, it has it's really an infinite dimensional vector, complex vector in Hilbert space. And we have another infinite dimensional vector in Hilbert space. So yeah, and then if you remember when we have derivatives, ddx, then we can replace this by IP hat. So then it actually turns out we can encode this whole system into a Schrodinger type equation, where now our Hamiltonian is acting on two modes. So this is a one-dimensional heat equation. Now it's acting on two modes. And the Hamiltonian has the form which is p squared plus v of x. So this is like the kinetic plus a potential energy that you normally have in a Schrodinger's equation. But now there's a tensor product, right, with respect to eta hat. And again, eta hat is like x hat, but then in another mode. So meaning that if we actually have a quantum system that naturally realizes this Hamiltonian, then you can simulate the heat equation like on a quantum mechanical device in continuous time as well as continuous space, because here we didn't discretize anything. So I'll stop at this point. Do we have any questions at this point?
Yeah, I can ask you a few questions. Yes. So first, is W like a Gaussian function?
Oh, very, very good question. So actually, it's very, very close. So we'll actually come to this in a bit. But since we're here anyway, I think it's, oh, what happened to my slide? Oh, there we go. So the initial state preparation is actually, because it's e to the minus psi, right? So that is not a Gaussian state on its own. However, we see that it is very, very Gaussian state. And in fact, it's very close to a squeeze state, but this squeezing, right, is like almost one, and which means it's actually very close to something called a coherent state. So this is normally the state that directly comes out of your laser. Okay, so, and actually we're doing experiments now. So we actually just use a Gaussian state. Actually, it's not a hard Gaussian state. Like we don't need high squeezing in this. It's just very close to a coherent state.
Oh, that's very exciting. Does it become the quantum heat equation as we quantized the variables?
Sorry, what was the question? Could you read that?
Does it become the quantum heat equation as we quantize the variables?
Does it become the quantum heat equation? I don't know what the quantum heat equation is.
Yeah, not sure either. So
oh,
yeah,
sorry. Yeah. So here, remember that we're using a quantum system, right? So that if we let this quantum system evolve naturally, then what we're saying is that the quantum state that we get out in the end, the amplitudes, and then we do some stuff to this quantum state actually. And we do something called post-selection, because remember we have to take the integral with respect to W at the end. So like we do something to it, and then the quantum state that would end up in the end, the amplitude would actually be the same, right? Or at least proportional to the solution of the real heat equation. So that's what we're doing here. I hope answers.
Yeah, sorry, I've asked them to clarify it. So if I get hear back, I will get back to you on that. How can this be implemented on a digital quantum computer?
Oh, yeah. So digitally, right, what you do is, again, it's the same kind of idea, right? Where, well, maybe it might be more useful. Yeah. So digitally, when you have derivatives, or maybe let me use it here. So when you have derivatives, right, like how do you solve like using classical numerical methods, like in a digital way, right? So there's no such thing as a derivative, like continuous way. You have, so depending on which numerical scheme that you use, we know a derivative is basically your function, a little spatial position, like say f of xn plus 1 minus f of xn divided by delta x. So that would be a very simple type of discretization. And then what you would have in the end would be a differential equation with very large, or a system of differential equations, which can still be continuous in time. So then you really apply the same principles, which actually I can tell you in a more general way. So the general methodology is that now what you've done is that you've now transformed your equation into du dt is equal to minus ia, but instead of now being a function of x hats and p hats, now it's like a super large matrix, right? Like after you did that discretization step. And this would be done on, and the way to do this now on a digital device, because now your A is this super large matrix, then to use Schrodingerization, then we know that operator, this large matrix, is in general not completely Hermitian, because if it is, you can just directly put this on a quantum device with that Hamiltonian. But if it has an anti-Hermitian part, as you would, if we have the heat equation, then you can actually write that in terms of it's both a completely Hermitian part as well as anti-Hermitian part. Then the corresponding Hamiltonian that you have, right, if it's the completely Hermitian part, that's A1, completely anti-Hermitian part, that's A2, then the corresponding Hamiltonian, you put that on a quantum device, it's H2 tensor product, eta hat, plus A1 tensor product, the identity. And this should make sense because if you only have A1, you already have Schrodinger's type equation, so you don't need this extra mode, okay, to help you. That's why it's the identity. But if it's completely anti-Hermitian, like you have for the heat-like equation, then this is why you need the tensor product with eta hat, as we saw with the heat equation example. But in the digital case, right, instead of instead of A2 and A1 being operators, right, as functions of x hat and p hat, they would just be very large matrices, which you break up into sums of tensor products or Pauli operators. Does that make sense?
Yeah, thank you.
So it's the same type of methodology, right? But yeah.
Yeah, I think we can keep going.
Awesome. So since we're this part already, you say, well, how do we do it for more general cases? And here I just talk about homogeneous, and homogeneous means that here we don't have a factor that doesn't depend on you. So we don't have a source term. And this is, then we do the same trick. Whenever you see x, you promote it to an operator. And this little subscript I refers to the quantum mode that you use. And classically, this refers to which dimension you're talking about. Because you can have space with respect to the first dimension, x of 1, or x of d, which refers to the x, the spatial variable with respect to the dth dimension. And each dimension side corresponds to a different quantum mode. Yeah, so it's the same trick. And then, just like what I say, you end up with essentially what looks like a differential equation, but now your A is made up of x and p hats. And again, if you digitize it, it becomes a very large matrix, but if you don't, you keep everything continuous, then this is an operator form. So it's an infinite dimensional matrix. And you have the completely Hermitian and anti-Hermitian part. And again, like I said before, the Hamiltonian, we have the form of A2, the complete anti-Hermitian form, tensor product eta hat, plus the completely Hermitian part, A1 tensor product, the identity. And then, of course, you can check the Hamiltonian is Hermitian on its own. Yeah. And then I think it would make more sense if I show you an example of how to do this, apply this trick. So suppose we have a d-dimensional convection equation, and this is one of the easiest equations. We actually have an experiment running actually on this. And here this is transport. So you're moving something and you're not changing the shape of it, you're just moving it. And here, remember the trick that we use. So remember x goes to x hat. And whenever you see a derivative, you promote it to an operator. So if a of j is now a constant, so it means it moves with constant speed, whatever initial profile you have, you're moving it across with constant speed. Then, of course, the scalar quantity is a scalar quantity, but now the derivative with respect to x hat, it becomes an IP hat, j. So which means that now we transform it into du dt equals to minus IHU. Now this has Schrodinger's form, where H, right, the Hamiltonian is AJ P hat J, which is automatically Hermitian. So in this particular case, we actually don't need an extra mode because the displacement is automatically of this quantum form. Okay. So now in general, simulations of PDEs that require entangling operations and ones that go beyond what we call Gaussian operations. So here if the Hamiltonian is only either linear or quadratic in your X and P, it's what we call Gaussian operation. And these ones can be fairly easy to do, or at least possible to do. But if you go beyond that, then that's something that we don't always know is classically simulable. And that would be important. All right, so now we know how to do this for this trick. And on the other hand, we can also go backwards. So if you already know the quantum system that you have, say a quantum optomechanical system, then you can go backwards and ask what kind of PDE it's most suited to solving. So now, which means you're demoting, so your x hat goes to x, but now your p hat goes to I, the derivative, ddx. So then actually if you go backwards and you say, well, a quantum optomechanical system of this form, now it's actually very suited to solving this Schrodinger-like equation, except now it has a convection term as well as a complex potential term. So you can go back and forth. So we also have examples with linear first order ODEs, and I realize I'm running out of time, so I won't go through all of these examples, but you can do this trick like Shor's equation, Fokker-Planck equation. Yeah, and we also have example hyperbolic heat equation. These are some of the experiments that we're doing. It's actually possible with something called the James-Cummings model. Yeah, we can do inhomogeneous PD, so this is where you do include a source term. You can also have high derivatives, which means that you can do the wave equation. Whoops. Yeah, you can do the wave equation, things like that. Yeah, so the basic idea is that if you have any linear system of ODEs or PDEs, can be put into the form on the left-hand side, where A is either an operator or a very large matrix, depending if you have ODEs or PDEs. And then you can break it up into its completely Hermitian or anti-Hermitian parts. And if you want to simulate on a quantum device, then this is your Hamiltonian. And of course, with the qubit representation, your x hat is the diagonal of a big diagonal matrix going from minus n to n, where n is your discretization size. And here you can go back and forth. And you know, this is another kind of flowchart diagram that we have, where given any linear PD, how do you embed it into your Qmodes? And then again, the trick x goes to x hat, the derivative goes to IP hat. If you have a kth derivative, it goes to IP hat squared. And then with Schrodingerization, you have your initial condition with the initial state, and then you have the corresponding Hamiltonian. And the way to implement it, I think it's very easy just to see on the schematic diagram, where you prepare initial state, where you have an initial quantum state, whose amplitude corresponds to the initial state to your original PD, but then you include an ancilla state, so an extra state which we said before is very close to a coherent state, which is a Gaussian state. And then you evolve it with respect to the Hamiltonian. And so you notice then, if you have a d-dimensional PDE, then you just need d plus 1 Qmodes. And so this is what I meant by not having this cursor dimensionality in this sense, because if your dimension is very large, then you just need d plus 1 Qmodes. It's linear in D. And in fact, if you find a Hamiltonian, A2 tensor eta hat plus A1 tensor identity, that is natural for your quantum system, then you just need one gate. So you just d plus 1 modes plus one gate. And then to deal with doing the integral, okay, to recover your u at the end, that actually corresponds to a measurement on your ancilla. And this is a post-selective measurement, and this is where you can measure the psi parameter, or you can measure the psi, and this is a quadrature. And this is actually very easy to do, say, for photonic systems. And you just need to select when your psi is greater than 0. And then you ensure that the state that you have at the end is actually the state you want to simulate. So u of t, which is a solution to your heat equation. Yeah, and then this is, oh, I realized that I've gone enormously over time. Yeah, so do we have any questions at this point?
We can always take a few questions, so please don't worry too much. And the recording will be made available online for anyone who has to leave now. So we can, if you have time, we can continue with a few questions.
Yeah, sure.
Yeah.
I just realized that I completely didn't have time for nonlinear. I actually prepared all 4 sections, but yeah, it went longer than I expected. Yeah.
I mean, we could continue now if you have availability and share with the students as a recording if they need to drop off. It is entirely
Yeah, sure. I mean, I'll be happy to continue. Yeah. So it's just that we did the survey and then and then I didn't realize that because when I give these talks, because I didn't realize the audience was going to be maybe so wide, because usually when I give the first part, it only takes me half an hour, but then I did a lot of extra talking, so my bad.
No, not at all. It's been amazing.
Yeah.
Just to everyone
Yeah.
online, please do not worry if you need to jump off. We are recording this and it will be shared with you as a recording. So if you do need to jump off, that is absolutely fine.
Oh yeah, no, please. I just feel that I promised something and I couldn't.
No, this has been amazing. Thank you.
I mean, only if you guys are happy to stay. Like because I'll be happy to talk about all like a little bit or all the other sections I missed like as well. Just if people want to know more, then they know like kind of what to ask. And then if you want me to share other materials as well, I'll be happy to do that. But I will go on the nonlinear one first for those who ask for it and would like to stay for it. But I do want to say something here about, so we talked about why analog is good. If we have used D+1 Qmodes and then we use one gate. So whenever it's possible, we should use analog quantum computing to simulate linear PDs. And then this is just like to go back to what we said before, where this bit belongs, that now we see how quantum analog things work. And what I mentioned about entanglement is that we see that Hamiltonian here, like A2 tensor eta hat plus A1 tensor the identity, you see with this tensor product, right, this is an entangling operation, right, between your ancilla mode, right, and ancilla mode, modes in general. So and so this is why we know that if we want to do this in a classical way, in general we can't, if we can't engineer these type of gates. So this is something very exclusive to quantum that we're able to do this. So now we see how quantum analog simulation works for linear PDs. So we have this PDs completely mapped onto a continuous quantum system, and no discretization here is necessary, and we see that the quantum cost is really linear in dimension. And again, the question that was asked before about digital, of course, we can also discretize this Hamiltonian as well. And then depending on properties of this Hamiltonian, like if it's sparse enough and the condition number and so on, and then you have quantum cost that is polynomial in dimension and logarithmic in n in the best case scenario. All right. So now you might ask, where is the quantum in all of this? So I mentioned before about entanglement, but there's actually something more than that. So these are some of the foundational questions, which is which PDs are actually classically efficiently simulable and which ones are not, and why we believe that this formulation makes it clearer, right? Or at least a way of finding out. And again, these are open questions, by the way. I'm presenting them just if you guys are interested, it would be great if you would like to work on them. So if we want to simulate, we want to use digital quantum simulation for this, then really we have all kinds of gates that are needed. So we have things called Clifford gates, and we have things called non-Clifford gates, and a universal gate includes both Clifford and non-Clifford gates. But what we know from something called the Gardner-Nil theorem is that if only Clifford gates and projective measurements in the computational basis are available, then that can actually be efficiently simulable by a classical computer. So you will need at least some non-Clifford gates. So for any quantum algorithm to at least not that we're sure that it's not classically efficiently simulable. Now, but if you do that for different kinds of PDs, it's really hard to kind of do this counting, right? And to see how hard Clifford gates are related to aspects of the particular PD. Because we do believe that there are some PDs which should be more easy than others, right? So it's difficult to see this. Now, we also have an analogous theorem in continuous variable systems by Bartlett, Sanders, Bronstein, and Emoto, where if you so your universal gate set for continuous variable quantum computing, they include Gaussian states as well as non-Gaussian states. And Gaussian states are kind of the continuous equivalent of Clifford gates. So if you only had Gaussian states, gates, and measurements, then they can be efficiently simulable by a classical computer. But here, if we use the Schrodingerization formalism, we can actually see exactly which PDs require Gaussianity and which ones don't. So then different PDs, right? You can see really we know which ones are easy and which ones may be harder because we need more non-Gaussianity. So, and because the formulation is so clean, right? So this is what I mean by simple algorithm, is that we can match kind of one-to-one, right? Which aspect, like the order of the derivative and the form of the coefficient and how they depend on x, right? How that maps exactly onto the Hamiltonian. So whether or not you're working with like a Fokker-Planck equation or Black-Scholes, you can see exactly where the mapping goes. So maybe then this will be a step towards trying to answer the more foundational question of which PDEs, which properties of these PDEs make it more classically simulable or not. So this is what I wanted to mention. Yeah, and then this is just a table of the different PDEs and so on. Now, oh yeah, and before I go on to nonlinear, I'll just mention a few benefits that I think of Schrodingerization, because I think you will hear a lot of other talks, right, about methods that are based on matrix inversion methods and block encoding or LCU type methods, etc. I'm missing a lot of references, by the way, but they're all in the papers. Yeah, so first of all, like one benefit is that we can take advantage of the continuous variable and analog quantum simulation. So meaning that we don't need to discretize a PDE at all. And then no discretization in time is needed, even if we discretize in space, which means that we don't, even if we use even if we use qubits, we don't need to break it up into many gates if we don't need to in a continuous formalism. And also we see that the formalism is easily adaptable also to the fully digital setting if one day we have these fully fault-tolerant digital quantum devices. And here we see that we avoid complications of matrix inversion methods where it depends on condition number for example, and other methods. If we can find the correct Hamiltonian, right, essentially we just need one gate. And also, as I mentioned before, we can see explicitly which part of the PDE, including the initial condition, right, requires entangling operations and which parts require non-Gaussian operations. So then if you want to answer the question, which PDEs are harder than others, we see from an analytical viewpoint that can maybe lead to deeper understanding than if we scramble up into lots of gates where we can't really tell the difference, right, by looking at the circuit, which PDE we're simulating. Yeah, so the formula is inflexible enough, not only for continuous variables and qubits, but also for hybrid systems, for both discrete and continuous variable hybrid platforms. And here we get the cost in D, okay, instead of exponential in D. All right. So now I will go, as promised, onto the nonlinear side. And then let me just stop at this page for a little bit. So I'll say that the idea is that problems, we say, become simpler by high dimension. So we saw with Schrodingerization already that if we just add one dimension to a homogeneous PD, linear PD, we make it into a Schrodinger PD. And we want to do the same thing for nonlinear problems, that we want to increase the dimension, but we can't increase it too high because again, that will make it inefficient. Just like us, we're already quantum, but if we want to simulate all the quantum particles that make up us, that would actually still be an expensive operation on a quantum computer. So we want to increase the dimension, but not too high. Yeah, and then the other two parts are about uncertain PDs and non-autonomous PDs, which I'll just briefly mention in the end for those of you who have more questions. But let me go straight to nonlinear first. Oops. Nonlinear. So how do we, so now if we want to simulate them on on a quantum device obeying Schrodinger's equation, we know Schrodinger's equation is linear. So this whole thing about simulating nonlinear ODEs and PDEs on these quantum devices is how do we turn nonlinear ODEs and PDEs into linear ODEs and PDEs? That's the basic question. Of course, there are so many applications fluid dynamics, gas dynamics, molecular dynamics, etc. So we don't need to be convinced about the power of these, but one of the important things to remember is that a lot of the difficulties that people have in the classical world is to solve nonlinear equations which are very, very strong nonlinearities, not weak nonlinearities, and that's very important. And some of the key things to note about nonlinear systems, which could be different from linear systems, is its unpredictability. So you can have a breakdown of perturbative theory. So for example, as a theorem by Bruns, is that if that perturbation theory converges in the neighborhood of one point, then you can show that it actually diverges at other points. This is a feature of very strongly nonlinear systems. And of course, you guys know about chaos theory. Okay, you would have heard about them. It makes them highly unpredictable. But also, there are appearance of discontinuities and shock solutions and singularities. So like vortices forming, for example, when you have nonlinear Schrodinger's equations and so on. And very often statistical methods are employed to understand ensemble behavior, and that will be something important for us to mention later on as well for our methods. All right, so first of all, we have to ask, is it possible to have quantum advantage in solving nonlinear ODEs and PDEs at all? But to address this, we have to ask, what do we actually mean by solve? What do we mean by advantage? And since we have to embed them into a linear system, how do we do this embedding? Or can we do this embedding at all? And just as a reminder, what we mean by nonlinear, so we mean that the functions here, f, in these ODEs and PDEs, that it's nonlinear. They're nonlinear functions of x or of u or its derivatives. And by classical solutions versus quantum solutions, classical solutions means you actually have the whole profile, right? But quantum solutions means we only have the state whose amplitudes, right, might embed the solution. So we haven't solved the full problem yet, but at least this is a very important first step. Most of the quantum algorithms that are out there is really to address the quantum simulation part. So, but since if we compare them one-to-one, we can't, and if we wanted to completely get the full profile in the quantum state, it's actually very expensive to recover the full state. But instead, what we want is that we want to compare observables only. Because a lot of the time, we might not actually care about the full solution. We only want to know something like, will we have an earthquake larger than Richter scale of 5 in this city at this time? So we just, or what is the average density? What is the average velocity profile in this region? So we want to know some observables. So then in terms of comparing observables, maybe we'll then have a chance of getting some quantum advantage. So, and again, with classical cost, we really mean numerical steps. With quantum cost, we might care about, if we want to do it digitally, we might care about query complexity. And with respect to parameters like little d, if we care about PDs, okay, dimension of the PD, capital D, which is the size of the system of ODs we care about, epsilon with respect to error, capital T, the time we want to do the evolution, and capital M, which would be, say, the number, right, of initial conditions. Because if we want to solve an ensemble of these problems with different initial conditions, can we also have advantage with respect to that as well? All right. So, but the first question is, can nonlinear problems be suitable at all, okay, for quantum computation? Well, we know, because we know that computation is a physical process, but the quantum computation itself, being quantum mechanical, by Schrodinger, is fundamentally linear. So what do we do? Well, then we have two routes that we can go. One is somehow make the problem look linear. So, yeah. And then this will be the bulk of the methods that's used. Or the other possibility is that maybe let's not use quantum mechanics, because even though quantum mechanics is fundamentally linear, right, we also have nonlinear quantum mechanical equations, right, like nonlinear Schrodinger's equation, for example. So there, it's not fundamental quantum mechanics, it is ensemble of systems like BECs, they obey the Gross-Pedievsky equation, which is nonlinear. And I'll just say that there are fundamental limitations to using nonlinear quantum mechanics, because like if you have high enough nonlinearity, if you have two states that are very close initially, right? If you use linear quantum mechanics, if they're initially close, right, and then they obey the same evolution, they will be close at the end. You don't change the fidelity because the evolution is unitary. But if you use nonlinear quantum mechanics, actually, especially if it's very highly nonlinear, then if you have two states that are initially very close, they become very far apart very quickly. And now there are algorithms. In quantum mechanics, there are fundamental algorithms, things called like quantum hypothesis testing, right? Where you ask the question, how many samples of the states are required in order to tell the difference between two states, which are not orthogonal to each other? Okay, so if you have two states that are super close, then in principle, you can use quantum hypothesis testing to tell them apart. But if you have nonlinear quantum mechanics, it means that you can tell them apart super, super quickly, which actually violates what we know from quantum hypothesis testing. So which means that it's not if you allow this possibility of using nonlinear quantum mechanics, actually it cannot be efficient because of the bounds that we have with hypothesis testing, which means that you cannot have two states that you can easily, right, become further apart and completely distinguishable, become orthogonal in a short time. It needs to take a long time. Right, so then we don't look at option 2, let's look at option 1. How do we make the problem look linear? Well, again, there are at least 2 ways of making the problem look linear. So one is approximating it so it looks linear, or an exact mapping so it becomes an exactly linear problem. So we have these 2 routes. And with approximations, so I know that there will be a talk later by, and a lot of the methods that are used in quantum algorithms for nonlinear problems and more general nonlinear problems are almost all approximations, at least for PDEs. At least for PDEs that you can show you can have an advantage in. So with, and by, of course, there are all kinds of approximations we can think about classically. So we have things like Taylor approximations. And then this is kind of, with Taylor expansion, you can think in this context, you can think about perturbative expansion. So it works really well when you're super close, but then when you have very, very weak nonlinearities, when you're very close to the origin, for example, but as far as you have any significant nonlinearity, right, then you're no longer very good. Another way of approximating things is that you can actually map, right, a nonlinear problem into an infinite dimensional linear problem. But to do that, you need to truncate it. So a lot of methods that are based on linearization techniques, like Kalman linearization and other kinds of linearization, they're of that kind, where you kind of like moment closure type of methods, you really do need to truncate your system. And in that case, you're losing information, but also they usually work for weak nonlinearities or where the time, right, you can only predict it up to relatively short time and not for a very long time. So I won't talk about those examples, but I think later on we have, so I think maybe Dr. Pedro Costa and others, they'll probably talk about some of these linearization type of methods. So what about exact mappings? So classically, what are the exact mappings that we know about? Well, something we know about in machine learning, for example, like kernel methods, we know that if we have a nonlinear separator, we can map it into a linear separator by increasing dimension. So that is one. But sometimes that also maps to an infinite dimensional system. And we do know that there is one example, one class of examples of integral systems, and especially for the 2D Burgers equation, there's a very famous example of being able to map exactly onto a linear system. And this is something called the Kohl-Hopf transformation. So, and apart from the Kohl-Hopf and Kohl-Hopf-like transformations, and these are for the integral systems, which are based on this Kohl-Hopf-like transformation. So not almost all other ones, apart from the ones I'm going to talk about now, they don't have exact mappings to them. So you would need to find approximations of some kind. But I will talk about one other class of examples where we do have exact mappings. So, and these are the nonlinear Hamiltonian-Jacobi and scalar hyperbolic equations. So I'll just say what these are. So these are, if you have your more generic looking nonlinear PD, now Hamiltonian-Jacobi, your nonlinear function f, right, is nonlinear function of the first derivative of u. And then for the hyperbolic, if you have some nonlinear function like h of u, then it's the gradient of this h. So so these are the 2 types of nonlinearities I'm talking about. So and what it turns out that we can actually have pretty nice exact mappings. So if you have d plus 1 dimensional nonlinear PD of either the Hamiltonian-Jacobi or scalar hyperbolic type with m different initial conditions, then if you have the nonlinear Hamiltonian-Jacobi PD, then you can actually map this exactly into delta dimensional linear PD that's of Liouville's type. So this is like a transport-like equation, things that don't really change the shape very much of the initial condition. And you can change the m initial conditions into a single initial condition, right? And where this delta is 2D plus 1. So plus 1 is just for time. So meaning we just need to increase the spatial number of dimensions 2 more. But we know that doubling the dimension on a classical algorithm, that's actually an exponential cost. Because remember, with the curse of dimensionality, your cost goes exponentially with the dimension. So d goes to 2d, that's exponential cost. But with quantum, right, we know that we don't have this curse of dimensionality. Well, if we want to do this in an analog way, for example, we can see this very easily. So then if we can simulate this the 2D plus one-dimensional problem in the quantum way, and now it's linear, it's possible we can use Schrodingerization and so on, then it can be efficient. And this is something that's called the level set formalism. And similarly with the scalar hyperbolic nonlinear PD, it can also be mapped to a delta dimensional PD, but we just need to increase the dimension by 1. All right, so that's the procedure we'll go. And then we hope to have a quantum algorithm that outputs observables to some precision epsilon. Yeah, so just briefly some applications: Hamilton-Jacobi optimal control, machine learning, geometric optics, etc. There are lots of examples. And I'll just briefly then mention what I mean by this level set mapping. So here we have a d-dimensional nonlinear scalar hyperbolic PD with m different initial conditions. And again, let's just introduce one more dimension. So this is our trick. We always introduce slightly more dimensions to make our problem look more simple. So we introduce a new spatial dimension chi, and we introduce something called a level set function. And how do we define this level set function? Is that this function phi is equal to 0 when the value of this extra dimension psi is actually equal to the solution of our problem. So this is phi that lives in this extra dimension, and when it hits 0, this extra dimension tells us the solution of this problem. And now it turns out that if you take this phi, this level set function, you put a delta function on that, you take a sum over all the initial conditions from k equal to m, then you end up with a new function called capital psi function. And it turns out that this particular psi function actually satisfies this linear transport equation. So you see this PD with respect to psi, okay, d psi dt minus the sum of ddx of x of psi, where the initial condition to this psi is now also the sum of k is equal to 1 to m of this delta function chi minus, okay, the initial condition of u. All right, so now we've actually increased the dimension, transformed everything to a linear equation. And then we can use Schrodingerization for this very easily. And just some quick observations that we have. So when your q is equal to when your capital Q is equal to 0, so here this is the q function in the original. So if we look at the first line, the q function in the nonlinear scalar hyperbolic equation, where q is only a function of u and not its derivative. If some quick observations, q is equal to 0, then you can have direct simulation without Schrodingerization. That's already sufficient. And we can kind of guess at this because this is like a transport equation. We already saw for the simplest transport equation, which is the convection equation, or the advection equation we saw very early, where we only need the Hamiltonian equals to IP. We saw that we didn't actually need Schrodingerization because it's already of Schrodinger's form. And if we only have linear hyperbolic PDs in this case, we only require Gaussian operations in that limit. And again, that means it's classically simulable. But if we have any nonlinearity in a hyperbolic PD, this is when we require non-Gaussian operations. So this is the potential for not being classically simulable. All right. And we do the same trick for nonlinear Hamilton-Jacobi PDs. So again, we have this level set equation, level set function. We put a delta to it, and then we sum over all the initial conditions. And here, the analytical solution to both phi, the level set equation, as well as delta of phi, satisfies this same linear PD that we see here, ddt of phi. And then we say, well, what do we do with this capital phi or psi function? Because it has all these deltas in it. What's the point of that? Even if we solve it, like, how would that help us? Well, this is a great thing about delta functions, because if we take inner products of delta functions and delta functions of the level set function with some other function g of p, what do we get? Well, we get the actual observable back. So meaning that we get expectation values of g, right, with respect to the solution, right, of our nonlinear Hamilton-Jacobi or nonlinear scalar hyperbolic equation. So as an example, our g function can be 1 or p squared, and then this inner product between the solution of our linear equation and any function g of p, that will give us, say, the first 3 moments to like density, momentum, and kinetic energy. And we also know that taking inner products in quantum is also something quantum is very good at. Because if we want to multiply a vector, like a column vector with a row vector, if it's a d-dimensional row vector and a d-dimensional column vector, then it's an order d operation. But with quantum, right, then we can actually reduce this to log of d. So taking inner products, meaning getting out the observable back. That is also something quantum is good at, right? Doing inner products. So yeah, so this is, yeah, so we have other examples. So this works well for high frequency limits of general hyperbolic systems. Right. So now what about general nonlinear PDEs? That's not either the Hamilton-Jacobi or the scalar hyperbolic type. Well, for general nonlinear PDEs, like I was saying before, it's really an infinite dimensional number of ODEs, if you want to be precise. However, since we can't do infinite number, right, we need to truncate at some level. And there are two kinds of truncations. So what we call Eulerian or Lagrangian type truncations. So Eulerian truncations is where you do the full discretization. And this is a lot of what people use, actually, where you have X and then you separate X into lots of little bits. But if you have two dimension, it's like you have a grid, right, of lots of little squares on your grid. So which means that if you have a little d-dimensional, d+1 dimensional PD, then it becomes a system of capital D nonlinear ODEs where capital D scales exponentially with little d. But you also have Lagrangian type kind of truncation, which is called a vortex type method, where now your capital D system of nonlinear ODEs is actually only something like d squared, little d squared in terms of the dimension of your PD. So now let's say if we have a system of capital D nonlinear ODEs with M initial conditions, is it possible to transform this into a linear PD? And the question in an exact way. And the answer is yes. We can do this in an exact way where delta is now D, capital D plus 1. So yeah, so depending on if you use the vortex type method or the discretization type of method, then it is still possible to simulate on a quantum device, but the cost, the difficulty part is really the truncation part. But after you truncated, then it is possible to completely transform your system D nonlinear ODEs into a linear PD of capital D plus 1 dimensions. So how do we do that transformation? So this exact mapping, you can think about like intuitively.
Sorry for interrupting, Nana. I know it's like really late for you, so I don't know how much more you want to go over. We can take a few questions and wrap up. I'll leave it up to you.
Oh yeah, so I'll just finish off this one and then it's yeah. So this is the last part of the nonlinear ODE part, and then yeah, then I can take questions. So yeah, so if we think about a system of nonlinear ODEs, then we can think it's, say, a system of D or N nonlinear ODEs. Then we can think about a system of N particles. So each of them having their own nonlinear trajectory. However, if we care about the probability distribution of this whole system of N, or this whole system of particles, then actually this probability distribution itself obeys a linear equation. And this is what we're doing here. So now this capital phi is, this product of these delta functions with respect to these particles. So then this delta function is really then saying this probability distribution. And then you can show that this probability distribution phi obeys this n+1 dimensional linear PD. And again, here you can use Schrodingerization or any other methods you like. And yeah. So then kind of the conclusion, right, is that if you have a d-dimensional scalar hyperbolic PD or Hamiltonian PD, then you just need d+1 or 2d Qmodes to deal with your problem. And if you have a system capital like N nonlinear ODEs, then you need n+1 Qmodes for your problem. Yeah, and I think, and then maybe let me just go to the final slide. So this is kind of a reference slide. So if you want to see some of the other applications that we have for PDEs that we didn't have time to talk about today. Yeah, and then I'll take questions because sorry, I went way over time, but I thought I should mention nonlinear.
Yeah. No, thank you so much. We really appreciate you staying over time and going into detail on everything. Maybe we have time for one last question, and let me just ask you like a high-level question. So in general, with the Schrodingerization technique, can you tackle Navier-Stokes equation and in general, like high Reynolds number flow? And kind of extending on top of that, like can you begin to study extreme astrophysical phenomena like active galactic nuclei, black holes, neutron stars, and so on? Yeah, can Schrodingerization tackle these kind of challenging problems?
So first of all, I want to say Schrodingerization is just a method of changing linear equations, right, into Schrodinger's type. So if anyone comes up with a super good method of transforming a nonlinear problem into a linear problem, then Schrodingerization can do any of that. So it's not a property of Schrodingerization whether or not it's able to handle linear or non-linear. Like the difficulty is really how do you get linear to linear part. So that's the first clarification. And talking about this, so in the methods that I talked about previously, right, in terms of translating the nonlinear problem into a system of ODEs, because as we know, Navier-Stokes type these equations, they're not of Hamiltonian-Jacobi or scalar hyperbolic. So they're a different class of problems. So we can't use these level set type of methods for Navier-Stokes equations or these plasma type problems. But yeah, so you have to discretize them, right? And then transform them into a system of linear ODEs. But you find that if you do that, even though you can, right, you won't get quantum advantage because your dimension is too high, like even in your quantum system. So using that route, I think we need cleverer methods. And I think currently a lot of what I've seen in terms of linearization type methods, again, I say that even classically, it's known that they work with relatively weaker nonlinearities, right? And then, or maybe they don't work with long time scales like you have with these like ensemble type methods. So I don't know of any existing system that is able to actually solve strongly nonlinear, right? Navier-Stokes equations or astrophysical phenomena. Again, these are very highly nonlinear systems in these strongly coupled limits. I don't know of any existing methods that can really successfully deal with them with quantum advantage. Yeah. But if someone does find an efficient method, right, meaning that they can map this nonlinear to linear problem where the dimension is not too high, right, then of course you can also use Schrodingerization for that or any other methods you like. But the difficult part is how do you transform this nonlinear problem in a linear problem such that the mapping is able to work for both very strong nonlinearities and large timescales, right? And then also the mapping does not increase the dimension too high. Yeah, so these are open problems.
Awesome. Yeah. Thank you so much. Again, once again, we really, really appreciate you staying over time and taking the time to answer all these questions. Thank you so much.